Yeah, hello. Am I audible? Manishankar, am I audible? Saurabh.
Yes, sir, you are audible.
So I think from today your offline classes will start. Let's wait for 2 minutes. Okay, only 10 students are here. Why so low attendance? Anup Kumar, Priyambada, Akash.
Yes, sir.
Why so low attendance today?
I don't know, sir.
Plenty of
Sir,
people know your new timetable.
sir, we don't get any notice about offline classes, sir.
Huh?
Hello?
Huh? What did you tell?
Sir, we don't get any notice about offline classes, sir.
Okay, let me start now. I think it's 12:01. So let me
Okay,
start.
sir.
Whoever will join, let him join. Okay, I think it's been recorded. Yes. Okay, so we're starting with module 2, control of DC motor drives, right? So first of all, we are going to see what are the basics of DC motor drives, what are the types of DC motors which we will be able to control, and then we will go forward. So basically, these are the contents of this thing. Then we move to types of DC motors. So DC motors, as you know, first of all, the most simple DC motor is the separately excited motor, right? Even many people of you have already seen this in the lab also, in the electric drives lab also. So this winding is the what? This winding is the field winding. So this winding is separately excited by this source, and the armature current is separately given from this source. I hope we have not done this
We
before.
have done this, sir. We are
Yes.
now we can
Up to which slide we did?
armature voltage control, sir.
Sure, voltage control. Up to
Yes,
this?
sir. So this one.
Okay, okay. It was quite a long time. Okay, so the speed can be measured. So the speed can be actually controlled by using the armature voltage control method. In this case, the field is kept constant, and this is kept constant. And then the armature voltage is actually changed. How do you change the armature voltage? Either with a chopper circuit or with the auto transformer and a rectifier circuit. Right. So what will be the drop? So what will the speed at no load? See the speed at no load. So this is the equation for the speed, right? So if you have no load, that means what? So if you have no load, this IA goes to zero. Armature current is almost zero. Then this term goes out. So whatever is left out is only this term. So this is the speed which we will get at no load. As soon as the armature current increases, what will happen? There will be a drop. And what is the maximum drop? This part is actually coming from here. So this is the drop which will come at the at the full torque, at the fully loaded condition, right? So this is how the armature voltage control is there. So armature voltage control is applied wherever you have to control the speed below the rated speed. Say below the rated speed, say you have a speed of 1500 rpm. Now you want to control the speed below this. So you will go for armature voltage control. Okay. Then some people may have the thought that if we add a resistance in series, then also we can control the DC motor speed. But thing is that this will be controlled, but the drop in the speed as the load is increasing will be severely high. See, for RL, this is almost this. So this is the minimum resistance that was. So this would be the drop. The more the resistance you put, the more will be the drop at that rated speed, at the rated tolerance. Sorry. So this is the problem with the armature resistance control. The speed drops very fast. So better go for armature voltage control. Why this is so? Because maximum of the energy is wasted as I square R, RA. Actually, this armature resistance is consisting of the minimum resistance plus that extras, whatever you add to it. Then comes the field flux control. So in this, we have a very interesting phenomena that if this is the field supply and we put a resistance here and vary the field current, then the interesting part is that Eg, which is proportional to K phi n. What is Eg? It is the generated EMF. So here we will put E back, that is the back EMF, so which is produced due to the flux and the speed. So if the flux goes down and EVAC has to remain the same, the speed will go up. Right. So if you decrease the field, then the speed of the motor will suddenly go up instead of going down. So this is a very strange phenomena, but this is mathematically correct. Intuitively, it doesn't sound so that it will do like this, but I have checked it myself. You can also try it in the Drives lab. There also, if you just decrease the field current, the speed will increase. However, there is a big problem that if you weaken the field too much, then too much of sparks will come in. And so this is very dangerous. So better don't go for separately excited motor. So we go for shunt type of DC motor. So this is a very important graph, these two graphs, whereby you will see the changeover of the torque with respect to speed in case of both the controls. So in case of armature control, what is happening? The torque is remaining constant. Armature voltage control. Right. So armature voltage control, the torque is remaining constant. This is the torque line. So this torque is remaining constant up to rated parameters, up to rated torque, up to the rated speed, the torque is remaining constant, right? But as soon as you want to go above the rated speed, then you have to go for constant power operation only. So power equals to torque into omega, sorry, speed into torque, right? So if you are actually increasing the speed, the torque falls down. Why the torque falls down? Because the field has gone down. Field which is a function of IF. If you decrease the IF, the field flux will obviously go down. Due to this, the torque also goes down. I think I will take you to a better slide. Okay, so actually torque obtained is a function of phi into Ia, phi F into Ia. Now if you decrease, so IF controls the flux. So torque is proportional to IF into Ia. Now if you decrease the IF, the torque will obviously go down. Is it not so?
Yes, sir.
So what will happen? The power goes to omega into torque. So if you increase, so if you increase the speed using the field control method, then the torque will go down. In such a case, the power remains constant. That is why in field control method, the power will remain constant and the torque will change. Right? So this is the meaning of this thing. Then we come to series DC motor. Can you tell me an application of a series DC motor? Sorry. Is it visible again? Yeah. So can you tell me the operation of a series DC motor? One very common application. Very common application. What is it? Any answers?
Self-starter in bikes.
Uh-huh.
Sir,
The
cranes,
bike.
Self-starter in
railway
bikes.
engine,
Cranes is okay.
railway engine.
Railway engine, a part of it is correct, not fully, because it doesn't operate totally
But
on the series motor. Sometimes it operates. Nowadays, it is not used also. Nowadays, only in induction motors.
Self-starter in bikes. Self-starter.
Yes, that is the most common application you will find anywhere. Self-starter of bikes and scooties also. Of any, nowadays every vehicle, every IC engine vehicle, it has this thing, series DC motor. So it will help to crank the engine. It's called the crank the IC engine. And it helps to crank it. Okay, so what are the basics of this? So let me show you. Just a second. Yeah. So in the motor we have this, say, RLE type of load, and for the separately excited motor, we have this extra supply for the field, right? So this is separately excited motor, DC motor, and then we have shunt type. Shunt is what type? Is we have the RL and we attach the field directly in parallel with the armature, right? But now we are having this DC series. Yes. So this is the DC series motor in which the field winding is kept in series with the DC supply. So this is very interesting. First of all, torque is proportional to phi f into Ia, right? Now this phi f is a function of which quantity? Phi f is a function of
IF.
If. Now in this series motor, If is equal to what? If is equals to what? The field current. See, this is the armature current, and this is the field current.
So it's called to armature current.
Yes,
Yes.
Ia equals to
Ia
If.
equals to Ia.
So the same current is flowing. So what it comes out as, the torque is proportional to Ia into Ia.
Yes.
That is, torque is proportional to Ia square. Right? So do you think this will be a linear motor? To draw a graph,
No. No.
will it be
Parabolic. Sorry, it's parabolic.
the torque will be, it will not be straight, it will not be straight, it will be something like this, Ia square, right?
Yes.
So that is the importance of this. Can you tell me a comparative value of the field windings in the three cases? Say, what would be this field RFB like? What will be the value like? Say this is 200 volt DC, it will hardly carry 1 ampere current, hardly. So what would be the resistance of this? 200 by ohm, 1, that will be 200 ohms. Here also it will be around approximately 200 ohms, 200 to 300, depending upon the motor. But what about this winding? What about this winding? Just a second.
Sir,
Yeah, sorry for the interruption. Some important call had come. Yeah, tell me. Yes, tell me. Any problem?
no, sir.
Okay. So what I was telling. Okay. So again that window is coming. Some of you please help me out in this thing. Okay. So let me clear the points. Phi is proportional to kf into Ia. Then omega is a function of V by. So what are these constants Ke, Kf? What are these constants? These constants are, say, the field constants. Say, so this is the kf is the field constants. So kf will be in the, it will have the unit of flux by the current, right? So if you can see it properly, omega is a function of V by Ke kf by Ia minus Ra by Ke kf. So the expression comes out like this. So if you draw it properly, sorry about the application, it's not getting removed. So this would be the speed and this would be the torque and this would be the nature of the graph. This is flux weakening zone. That is, it is going into a sort of constant power zone. Say if it is at this point, say point A, say what is the speed here? Omega. What is the torque here? T1. Now if you decrease the speed, the torque will increase. So you cannot decrease the speed, right? You have to increase the torque. If whatever that T2 will be, as per that the speed will come down. Doesn't that happen with everyone? If you are riding a bicycle and suddenly one of your friends jump onto your bicycle, so your speed goes down or not? Hmm. So this is a comparative study of all the type of motors. Say this is a separately excited motor. This is very much straight. So this is very good type of waveform. This is a completely linear shape, right? Does it not have a completely linear operation? Yeah, please mute yourself, whoever it is. Thank you. So, so this straight line is a very linear type of thing. So that means it is a very easily controllable motor. And then speaking about this one is a compound and this one is a series. So do you see this curve of a series motor? It is so much high. So what it is said that a series motor should never be started on no load. So what will happen if you start a series motor on no load? This is a very good interview question. So tell me what could happen.
Sir, it will rotate at infinite speed.
So infinite speed cannot happen, right? But physically it will reach to such a high level of speed that all the parts will tend to fly out. Right. So it's, so never start a DC series motor without a load. So that's the lesson. Okay, so I have to go to the next PPT. Just wait.
Sir, can you explain that with a formula?
Which one?
That series motor should not be started with no load.
No, no. Okay. So if you have no load, so what will happen? First tell me. Just tell me that. Forget the equations now. First of all, come to the. Uh, just a second. Yes. Okay. So, what would be the equation of a series motor? What would be the equation of a series motor? So V armature, whatever I give to that will be equals to I F RF plus, so this would be the in the steady state. Actually then E back, no, IARA plus E back,
Feedback.
right? So now IF is equals to IA, right? So IARF plus IARA plus E back. So let me go to this thing. So IA you take common RA plus RF plus E back. So E back will consist of VA minus E back. So E back will be K phi N by IA will be equals to RA plus RF. So what are we comparing? What was the problem? The problem is that if you give no load, right? If you give no load to it, then what will happen? No load means the armature current will tend to zero. Is it not so? So you have to find a relationship between the N and IA, right? So what I will do, I will just do some modifications. RA plus RF is equals to IA. Tell me now. So if IA goes to zero, what will happen? Are you there? Am I connected?
Yes, sir.
Yeah. So if you are giving no load to it, that means what? The armature current tends to zero.
Hmm.
Is it not so?
Yes.
It will not be zero, but it will tend to be zero, right? So if it goes to zero, tends to zero, then what will happen? RA plus RF is, can it go to zero? No. So the numerator will tend to go to zero. Then the numerator here will tend to go to zero then,
Yes, sir.
right? So VA minus K phi N should tend to go to zero, right? Now you already see that the flux is less. Why? Just a second. K equals to K phi N. Then K is into K1 into IA into N. Is it so? Bit of messy things. Just a second. I will clear some parts. Please mute yourself, whoever it is. Disturb the class. Yeah. So, but phi is produced by what? The flux is produced by what? The armature current only, na?
Yes, sir. I am.
So we can attach another constant K1 into IA, the flux for, yeah, for this flux, right? Now I is tending to zero. So who is the one quantity which can make this term equal to VA? Anyone left? K into K1 IA N I is tending to 0, will the value of k and k1 go very high so as to make the left hand side equal to right hand side?
No.
Just a second. Have you come to this conclusion first of all? Tell me. Have you come to this conclusion? What was the equation? V armature was equals to what? IA into RA plus IF into RF plus E back, right? So I is common for that, RA plus RF plus this is K phi n, this is VA. Now we need to find the speed. So VA minus K phi n divided by RA plus RF will be equals to IA. Now if it is at no load, almost zero load, that means IA will go to 0, right? So out of the numerator and the denominator, which can go to 0?
Numerator.
And numerator. So
Numerator.
VA minus K phi n
Phi n
must be
tend
equal to
to
0,
Yes.
tends to 0, not 0. So VA should be equals to K phi. Now phi
Phi
can
n.
we write as some another constant K1 into
IA.
IA only, because IA is the field current only, right? So tell me, now IA is going to 0, right? This IA is already going to 0, right? Is it not so?
Yes, sir.
Then who is the one quantity which can pick up this left hand side
N's.
equal to right hand side?
N's. N.
N, only
Yes.
n, right?
Yes.
So n should go to infinity or a very
Okay.
large number.
Yes, sir.
So did you get the answer of your question?
Yes.
So if IA tends to 0, the speed tends to infinity. So that's why this is proved now. So is it okay? Or should I explain again?
Sir,
Yes.
in practically the speed would not go to the infinity. So what is the maximum speed that it can go?
See, if it were you, what would be the maximum speed at which you could rotate? Tell me. Consider yourself as a DC series motor. Could you go to infinite speed?
No.
Huh? Could you
No,
surpass the speed of the light?
definitely not.
So mechanically, how much is possible for a thing to rotate?
Sir,
Unless the parts fly off. The centrifugal forces destroy the motor,
Yes.
right? Yeah, tell me. Any other person?
sir, phi, what have you replaced it with? Phi?
Phi is basically produced by which quantity? This phi, the field flux is produced by IF, na?
Yes, sir.
Field current. Now, so we can write this K1 into IF, and now IF is equals to only IA.
Hmm.
So that's what it is. K1
K1
into
in
IA. Yes. So K and K1 are different constants. So they are dependent upon the machine. So they cannot change.
hmm.
Right. So what can change? IA and N is there only, na? If IA goes to 0, N has to go to infinity. Means if IA tends to go to 0, then the speed has to tend to go to a very high speed. Then only the voltage will be equalized, right? So is it
Yes, sir.
fine? Yes. So just copy it out or have a screenshot of it, whoever asked the question. Okay. Okay, so I will go to the next slide. Just a second for that. I'm trying to find it. Okay. Is it visible? No. Yeah, operating modes of DC motor. Yes, yes, now it is. Is it visible?
Yes, sir.
Yeah. So we will now go to the operating modes of a DC motor. So you must know at which modes the motor is working at. So basically, what will be the common sense here? If you have a vehicle, right? If you have a vehicle, so it's a car type of thing. Sorry for the drawing. So if you have a vehicle, what will you do first? You will start the motor, start the vehicle. Starting the vehicle means starting the vehicle's motor, right?
Yes, yes.
And then you will accelerate. Then sometimes you will have a constant speed, right? And within the constant speed, you will sometimes speed up and speed down, right? So that would be the speed control,
Hmm.
right? And finally, when you reach home, you will try to brake the
Vehicle.
vehicle. So this will be braking, right? So in general, we have to know what are the starting methods of each type of motor, whether it is DC or AC. Right now we are concentrating on the AC, on the DC part, so we'll know what are the starting methods, right? So once we know the starting methods, then we start the motor, and then we have to know what are the speed control methods, how we will change, how we will have a control over the speed, and finally we will see what type of brakings are available for this motor and what are the advantages and disadvantages of it. So is it a fine story you want to hear?
Yes, sir.
So just consider yourself sitting in the vehicle, and you start the engine, start the DC motor, have a speed control up and down, and then you will finally brake, right? So let's begin the journey. Just a second. Yeah. Yes. So starting, right? Then motoring. Starting means it will draw power from the source. Then we have the braking things. So braking takes into account three things. Second. So braking takes into account three things. The braking is first of all, this is dynamic braking. Second one is plugging action. Finally, we have regenerative braking, which everyone is aware of right now, right? Everyone knows this term, na?
Yes, sir.
Regenerative braking. Whatever you don't know is only dynamic braking and plugging. And this four quadrant operation, we will also see it. So what are the operating modes? That standstill, if a motor is started with full armature current, a very high current will flow. So have you do you remember this thing, that a DC motor should not be started at full voltage? Directly should not be started. It should be started through a three-point
Starter.
starter.
3.8.
Three-point starter. Why?
Order.
What is the reason? What's the reason behind this?
To control the starting currents.
Control the inrush current. Actually, what happens when you are giving so much high voltage? Say you are giving 100 volts. You are giving 100 volts here. So when suddenly you are giving a 100 volts, then the motor has not started, right? So the back EMF, which is a function of k phi n, since the speed is almost zero, the E back is almost zero, right? Now whenever you start this, what happens? The only thing which is to limit the current is this armature resistance. Say this is in the range of 0.5 ohms. So can you imagine what would be the current through it?
Very lots.
100 by
Very
zero point
huge.
0.5, 200 amperes. So if the
Yes.
supply is not able to supply 200 amperes, what will happen? The fuses will blow out. Either the fuse will blow out. If the fuse fails to blow out, then this entire motor will get burned,
Yes.
right? The brushes will get charred, right? So all the distractions will start happening. So what we do? We give a big
Order.
big resistance, starting resistance, and then slowly we cut out the resistance, right? So that's what we called as 3-point starter.
Sir, why 3-point starter?
You can make it 300-point starter also. What's the problem?
So man, I mean 3-point must be having some significant.
You find it out. You can have 4-point starter also, 400-point starter also. The more number of points you have, the smoother will be the starting of the motor, right?
But the circuit will be bulky.
Yes,
So
definitely.
if you put 400-point starter,
Definitely.
the circuit will be very bulky.
Definitely. At least the 3-point has to be there, na?
Yes.
At least 3-point has to be there. Why? Now, if you have a resistance like this, and then you have the motor like this. So if I attach this here and the next point I give it here, so what is the wind? So what is the significance then? It's the same thing now. So at least three points has to be there,
Yes.
right? So I think that's the reason why it's called at least a 3-point starter. You may have 300-point starter also, right? That means you will have 300 points over this region, but that would be a waste of time, right? Because this resistance is active for only hardly a second, so it doesn't matter so much. So you just start it like this, and then it automatically gets cut out. So these are mechanical things. It's very difficult to build on mechanical things. If you have a chopper, I would prefer to go for 10% duty cycle first, then 15% duty cycle first, then slowly increase. After 50% you might take it directly to 100%. Don't you think so? If I would use a if I would have used a chopper, DC chopper, what would be the advantage? There we wouldn't have needed this 3-point starter. We'd have decreased the duty cycle to as much as 5%, say. After 5%, 10%, 15%, like that, we would have raised it to 50%, then we would have a jump to 100%. Once the back EMF develops, we can have a jump, right? So in that case, we would have, say, 100 by 2 means 50-point starter also, right? So that's the thing. So do you get the basic sense of it?
Yes.
Any others having any doubts, please speak out. Don't
So
worry.
that second point, sir, to limit the starting current to about 2 times the rated current.
Which one?
So that second point, to limit the starting current to about 2 times the rated current.
You can have more points. You can have a 4-point starter also. It will depend upon the how big is the motor, right? How big is the motor? It will depend upon that. So you have a very large motor, as large as, say, a big chair, say 30 HP motor. So then you would have gone for much more points, right? You would have gone for at least 5 points or 6 points, right? Okay, so this is the thing which I was sharing first of all. So this would be the thing, point starters, right? Slowly it would have cut out. So this would be the speed versus the armature current relationship for this. On each switching S1, S2 gets closed, the graph would shift. Okay, so operating modes of DC motor. Now we come to the motoring part. Now the motor has started, right? Now how will we motor it? So separately excited motor first of all we consider, then series motor we will consider. So back EG is less than supply voltage. This is the main condition for motoring. Motoring means what? The current has to flow into the motor, right?
Yes.
Now for this to happen, what is the minimum condition? Say this is the EG.
Back
This
EMF must be less than
is
supply voltage.
say this is 200 volts. So this is 220 volts DC. So this VA should be greater than EB. At least then only the motor will accept power, will accept the current, right? So this is the minimum condition for the motoring mode to operate. Then both armature and field currents are positive, and motor develops a torque to meet the load demand. So where is the load? The load will be situated on the armature, the shaft of the motor, right? It might be a vehicle, it might be some other type of loads, depending upon the application. So it will develop a torque. This torque will be proportional to phi Ia, phi f into Ia, and this should be equals to the load torque for constant speed operation. If you are not accelerating, if you are just having a constant speed, then this must be the equation, right? This must be the approx equation actually.
Yes, sir.
This TL plus some amount of this frictional load and all the windage losses are there. But neglecting all those things, this TG should be equals to TL, right? So separately excited motor. So uh, not for this. So it's for this. So in the series motor, if you go for braking, and in the separately excited motor, if you again go for braking, we have to make these following circuit changes. Let me show you in a different screen. So we are talking of braking now. Right? So seems that you have reached home, for which you need to brake. So what types of braking are available? Braking. So first of all, you are running your motor with say 220 volt DC coming off from a battery or somewhere. So this is the motor. The back EMF was 200 volts DC, and it was just a second. Again calls. Sorry for the interruption. Okay. So what I was talking of, we are talking of the separately excited motor. So this was the separately excited motor, which was having a resistance. Now, say this separately excited motor, this field resistance is constant. This field intensity is constant. Now this is 220 volt DC. Now I want to break it. What will I do? First of all, I will get this power out. I will switch off the power and I will connect the motor to a resistance. So this is now cut out. So what will happen if I connect it to a resistance?
Current
Will
will
there
go
be
to-
any current flow? Don't you
current will
think
go-
the rotating inertia of the motor will actually generate some EMF,
Yes,
Yes.
sir.
same EMF, and due to this, when it is getting a closed path, a reverse current will flow.
Will be yes.
Now torque was proportional to phi into Ia during the motoring mode. Now the current has reversed, but the flux has not. So flux into minus of Ia,
Yes.
right?
Right.
That means what? The torque is now negative,
Hmm.
right? So the torque will now go negative. So even if the motion is in the clockwise say, but the torque will now go negative. So that means it will tend to brake the motor.
Yes, sir.
Yeah. So that is what we call as dynamic braking. Dynamic braking, this resistance is actually connected. Now, what is the advantages and disadvantages of it?
Sir, there will be losses, sir. There will be losses.
Yes, the whole kinetic energy of the motor, will get dissipated in the
Yes, yes.
resistance as
Yes.
I square R
Last.
Yes.
Yes.
loss,
Hmm.
right? It will whole get dissipated as square R loss. So what is the use? The use is that it is very simple.
Yes, sir.
It
It's
is
not
very
much
simple.
complex.
It is not jerky. No circuits are involved. No power electronics. Nothing is involved. In fact, right? So it is very simple. Just connect our resistor, and it will keep on. It will start breaking, right? So this is definitely not used in vehicles because it would decrease the mileage.
Yeah.
Right? So this
Yeah.
is used in very big, large type of motors where the inertia is very high, and the people are not worried about the power and all those things, and the people want a very cheap solution. Then they can connect a easy type of resistance here, and then it will break out. Right? So this is one type of braking. Now, if you want to do the same for the series type of motor, what would be the changes in circuit? So that is
So the
very
previous
important.
slide, sir.
Huh?
So previous slide.
Yeah, I'm doing that only. Don't worry. So say you are running a series motor by chance. So this is a series motor, B input, and the EMF was in the range say 100 volts, and you are giving at 110 volts DC, and you are running, right?
Yes.
Now you want to break it. So first of all, you will get this power supply out,
Yeah.
right? So torque proportional to phi into Ia was the motoring torque, right? Now you want to brake, so you attach a resistor here. What will happen? The current will reverse now, armature current, right?
Yes, sir. Due to inertia.
But you again see that if the armature current reverses, the field current also reverses.
Yeah.
If the field current reverses, it will eat up the residual magnetism. I hope you know the story of residual magnetism. Huh? BH curve. So it will say it is operating here. If you just reverse the current, it will try to go here. And this would be the
More long.
residual mechanism. This would be the residual magnetism, but it will eat up this up to here, and then it will not go in the reverse direction because no back EMF will be produced. So essentially, you cannot reverse the flux. Also through the equation you see, if you reverse the flux direction and the armature current direction also, then motoring is also happening because minus into minus is equal to plus. Don't you think so? So this cannot happen. So what do? You have to keep for the braking, you have to keep the field in the same direction and have the current in the negative direction. Then only you will have the braking torque. So what do you do for this? What do you do to make this happen? Say this was A point, this was B point. So what you do, you just reverse, B and A point. I just connect it in the opposite side. Just a second, let me draw it in a better way. So what do you actually do? You are running your motor. Like this. And now, what do? You connect it like this. Is it nice? Now A and B. In this way, you can just change the connections. So in this way, the armature current will be flowing out of the motor, but it will maintain the same direction. Say it is. Did I make a mistake? Yeah, it is correct. So in the motoring mode, the current was flowing from A to B. Is it not so?
Yes.
In the motoring mode, current was flowing from A to B, right? So you must maintain this direction of current same. So say now you are in the braking mode. In the braking mode, you have to again pass the current from A to B. Is it happening here? Is it happening here?
Yes, sir.
Just check out the connection. So it is going here, here, and it is again going from A to B, and then again it is coming out, and then it is being dynamically braked.
Yes, sir.
So the current direction is same. That means torque is proportional to the same direction of flux, but with a negative armature current. So this would break the motor. So this should be the change for breaking a series motor dynamically. So is it okay now?
The current is in negative direction.
Yes, current is negative direction with respect to the first one. Say this was in this direction.
From current is from A to B, and in this case also A to B.
Armature current. You just observe the armature current. A to B is the field current. Field current.
And that is only armature current, right?
Yes, but see it from this perspective. See the armature current going out of the motor here. Torque does not depend upon the names, right? Torque will depend upon the direction of flux the field is throwing and the direction of the current that is flowing through the motor terminals. So you see this point, armature current is coming into it, coming in, right? And this is going out. Is it not so? See, the torque is where happens. Torque is happening where? Torque is getting generated inside the motor. Due to what? Due to the Lorentz force, right? So torque will depend upon the flux in the direction of the flux and the direction of the current. That is the current through the current carrying conductors. Current carrying conductors which are in the windings inside the motor, the direction of that, right? So you have to consider this current is going out or coming in. So this torque will be negative
Yes,
torque.
sir.
Now is it good enough?
Yes.
Yes, sir.
Deep, is it okay?
Yes, sir. Yes, sir.
Somaya, done? Yeah, please keep on asking such questions, right? So dynamic braking for separately excited motor, this is the circuit and this is the VI characteristics. So you have these PPTs, I think, already with you people in the contents page. So still, so this would be the motoring. So everywhere, whether it is motoring or braking, it is completely a linear thing. See, it is linear. That is why people love this DC motors. They are very good for controls. Okay, so the braking is also linear, the motoring was also linear, right? Then we go for series whose characteristics is obviously non-linear. See, this would be the motoring side and this would be the braking side. So both are non-linear. So torque is proportional to Ia square, whether it is braking or whether it is motoring. So that's why it's a non-linear. But still it's a DC motor. So dynamic braking will work even when supply fails. Is it not so?
Yes, sir.
So that's the biggest advantage of dynamic braking. Even if the supply is not there, you just connect a resistance. Simple resistance. You connect and things will start to work. If you don't have a resistance, put salt inside the water and then put the two terminals inside it. That will act as a resistance also. Then also it will work. And then we come to plugging. So plugging, I think we can start from the next class. Right.
Sir, can you revise from starting once again?
Yes, yes. So should I start from here? I think this will be good. Discard it. So see, we are on a journey, right? We are on a journey, say from Bhubaneswar to a power plant, right? Now we are on an electric bus, say, right? So we are on an electric bus and we are a member of 50 students, right? So first of all, the bus has to start, right? The bus has to start, right? So for the starting, we need to have knowledge of the starting methods. We cannot start a DC motor just like that. If you give full supply to it, then it will go out. So we need to
Yes, sir.
starting methods, and then once we have started, we need to sometimes speed up, sometimes speed down, sometimes speed up, sometimes speed down, and finally we have, when we reach our destination, we'll brake, right? So the whole of electric drives is considered with starting methods, speed control methods, and braking methods. Does that make sense?
Yes, sir.
So first of all, we will learn starting method. So what was the starting method? Like a 3-point starter, right? For a DC motor. And then for the speed controls, we have two styles of speed control. We have, say, for the rated speed of 1500 RPM. So we have a rated speed of 1500 RPM. If we want to have the speed control below that, we'll go for armature control, armature voltage control, right? If you want to have a speed higher than that, we'll go for field controls, field supply control, right? And for braking, we have 3 techniques. Dynamic braking is there, we just now learned. Plugging is there, we'll see to it later. And then regenerative braking is there, which we have learned way before long. Is it not so?
Yes, sir.
So these are the methods which we will learn. Now let me take you. So starting, motoring, dynamic, plugging, regenerative, and finally the 4-quadrant operation. So this is the picture for that 3-point starter. You can have more points. The more points you have, the more smoother will be the
So can you explain me
starting.
the second point here, that to limit the starting current to 2 times the rated current, that line.
To start to 2 times the
To
rated
limit the starting current about 2 times the rated current. I mean above that what happens, below that what happens?
See what is called a rating. Do you know what is how a rating
Maximum
comes up?
current that a machine can operate
Operate at, right?
at certain frequency.
So DC does not have any frequency. Mind it. Okay, say let's consider it as a separately excited motor, the simplest one. So here we have the DC field windings, right? And now we have a input voltage. Now what I do, I just suddenly give 220 volts DC. What will happen? Tell me. Say this is 1 kilowatt motor. How much will be the current, rated current? How much will be the rated current for 1 kilowatt motor? So this is 200 volts, not 220, 200 volts. So power is equals to V into I. So 1000 watts, voltage is 200 volts into I. So I is maximum 5 ampere,
Yes.
right? But initially, if I turn on this and the armature resistance is only say 1 ohms, which is a very obvious choice, right? Say the armature resistance is only 1 ohms, then what will happen? The E back at initial level is 0. What will happen? How much will be the inrush current? How much will be the inrush current?
5 ampere.
5 ampere.
Who will limit
5
that 5 ampere? Who will limit that 5 ampere? We should limit it to 5 ampere, right? We should limit, means we should limit it. But if we just start it with a simple switch at 200 volts, I am directly switching it on, dual starter, direct online starting. then what will happen? The back EMF is zero at the point of starting. What will be the current? 200 volts divided by 1 ohms.
Sure.
Why 1 ohms? The armature resistance is the only limiter there.
Yes.
E back is not there because initially the motor is at 0 speed. Is it
Yes,
not
sir.
so? So how much will be the current? 200 ampere. Just think of it. We should have limited it to 5 ampere. And how much current we are flowing now? 200 amperes. How much times more? So will the motor stay?
40 times more.
So it will burst out,
Burn out.
right? So how much extra resistance we should put out? Say 1 ohms plus some extra resistance in between,
Mm.
so that it will be approximately say 2 times of the rated current, 2 into 5, say
It is
10.
200.
So how much will it be? R plus 1 is equals to 20. So R
19.
will be 19 ohms. Now, how will you plan this 19 ohms? How will you operate this? So you will extend this and you will have some points over here, right? Say up to here it is 19 ohms, then you will slowly cut it, right? So first, so at a bigger thing, say this up to this is 19 ohms from point A to B, then point say C it is some lesser ohms, and then D it is still lesser, then E it is still lesser, and then you will slowly cut it out, right?
Variable
Are
resistance.
you getting a sense of it?
Yes, sir.
Right? So in this way, the resistance has to be planned. So if you want to limit it to say only say up to only the rated current, then what will it be? This two will not be here. It will be one here now. Is it not so?
Hmm.
So it is up to you how much you want to limit the initial starting current to. It is up to the engineer who is designing this, right? So this would be the fundamental principle of it. Hope you had a sense of it.
Yes, sir.
Yes. So operating modes, motoring. So that was the series and this one. So EG has to be less than the supply voltage. And then for the dynamic operation, this would be the connections, and you have to reverse the series motor terminals, the field terminals, not the armature, right? Then dynamic braking, this is the characteristics, omega, speed torque characteristics. And for the series motor, this is the speed torque characteristics. Why non-linear? Because in series motor, it depends upon the current square. The torque depends upon the current square. And final point is that in dynamic braking, it will work even when there is no supply,
Right. Yes.
because there are already, right? So from the next class, we will start plugging action. Right? Okay. So any other doubts? Any other doubts? Okay. So meet you in next class.